In this video, we're going to take a brief look at a few properties of the set operations that we previously defined. So those operations include the intersection, the union, complement, and so forth. We're going to look at some pretty simple properties that are associated with them. And in fact, it's essentially one big theorem that we're going to state today. And now the theorem, it has several conclusions, and we're not going to get into the proofs of all of them. I will illustrate one, a proof of one of the parts. So let's get into it. And what I'll say is, give it a theorem, and yes, it's basically a set operations, and it's going to be, so let U be our universal set with A and B subsets of that universal set. Let's say where A and B are non-empty, right? In some cases, you can drop that requirement that they're non-empty because the empty set is technically a subset of all sets. But just to simplify some of the ideas that we're going to present, we're going to assume that we have a universal set, and then A and B are non-empty subsets of U, right? So then what do we have? So I'll go, like I said, there are quite a few of these properties. Many of them are fairly simple. And I'll start with a couple that are called identity properties or laws. So for instance, if you take A and union with the empty set, right? Remember, you can denote the empty set like that or with the empty braces. What you're going to end up with is A, right? And then similarly, let me go ahead and just list them vertically. If you do A intersected with the universal set, you're going to get back A, right? So the first property here is saying take all the elements of A, all the elements of the empty set, for which there are none, and you put them together, right? And then you get, obviously, you're just going to get back A. This property is saying if you take set A and find all the elements that are in the universal set and A, those will be precisely the elements of A. Because remember, the universe for us contains all the elements under consideration. So U has all the elements, and then you're finding all the elements that it has in common with A. Well, that would be all the elements of A, right? So these are called identity laws. Let me continue our list. So our third property here is saying if you take A union with the universal set, you're going to get the universal set. And then fourth one, if you take A intersect with the empty set, then you're going to get the empty set, right? So basically and these two, again, and the reason I'm not writing them down is that you're not going to be necessarily quizzed, or, you're not going to be required to state what each of these properties are. But these 3 and 4 are called domination laws, right? So like for the union, the universal set dominates all the other ones, right? And then for the intersection, the empty set dominates all the other ones. So the one that dominates is the end result, right? 5, and so 5 and 6 are going to be things that that make a lot of sense. And this one I'll actually write down the name because it's named in a similar manner to an arithmetic property for numbers or an algebraic property for functions. And these are the commutative laws. So if you have A intersect B, it's the same as B intersect A. And similarly, 6, if you have A union B, that's the same as B union A. So these are the commutative laws or properties of set operations, right? Both the union and the intersection obey these laws, right? So these are commutative laws. It's very similar at, x plus y is the same as y plus x, or x times y is the same as y times x, properties that you're used to with real numbers and complex numbers, right? So those are commutative laws. Nice thing is, we have associative laws too. And remember, associative laws are ones that allow you to perform the operation repeatedly. So on more than two elements, or well, in this case, I should say sets, right? So let me state it for the intersection. So it says if you have A intersect the quantity B intersect C, turns out it doesn't matter how you group them, right? In other words, with the parentheses here, it's saying that you'd perform this intersection first and then take that result and intersect with A. Well, it turns out you can change the grouping. You can find the intersection of A and B and then intersect with C, right? So that's the intersection version of the associative law. And then here is the union version. So what are we up to now? 8. Actually 8 in terms of Roman numerals. Actually, yeah, it is right. I think it's like that. If not, you can correct me. It might be this. Either way, that's 8. And so it's saying that if you take A union the quantity of B union C, notice it's same operation all the way through, then this is the same as the quantity A union B union C. These are the associative properties. They have to do, or laws, they have to do with the way you group things, right? And what this is saying is, so basically what these laws are saying is that if I write down an expression like A intersect B intersect C, there is no ambiguity here, right? No ambiguity in the sense that I can choose how to group them. I can choose to group them like this or like this. It doesn't affect the result, right? And that's the beauty of these properties. And it works for unions and intersections, all right? Property 9, what do we have there? So now, if you think back to your properties from algebra, you have associative, you do have the identity property, right? And we don't really talk about domination properties in algebra so much, but you do have identity, you do have the commutative properties, you do have the associative properties, but a really big one from algebra is the distributive property. And it turns out we have similar properties for sets as well. And this is one version. There are two versions of it. So if you have A union the quantity B intersect C, notice the difference with this expression is that this expression involves two different set operations, the union and the intersection, whereas each of these involve the exact same operation. So now we're looking at, like, algebraically, how do we combine these two, right? Or how do we make sense of this? Or what's another way that we can write this? Well, it turns out this is equal to A union B, that quantity, intersect A intersect C, right? So this is technically the distributive law of the union over intersection, right? So we can essentially, in a sense, you're distributing the A union to the B, and then the A union to the C, and you're keeping the intersection there, right? But it turns out we can switch these two, and it works. There's a similar version. So if I have A intersect the union of B and C, then this is the same as A intersect B union A intersect C. Let me see. Yeah, A intersects C. So I think I wrote something wrong in this one. This should be a union because it's A. I think I said union but wrote the intersection, right? Okay, so these are our distributive laws for our set operations, all right? So yeah, those are some pretty useful properties. As promised, I said I would show you the proof of one of these. Well, actually, in fact, before we do that, there's one more. In fact, these are the one of these. I'll show you the proof. Let's see, for number 10. Notice none of these properties so far illustrate the complement rule. So I'm going to give you a couple properties that involve the complements, and some of these are really common sense. But like if you have a complement and then you take the complement of the complement, you're going to get back the original. 11, if you take the complement and intersect with the original, well, you'll get the empty set, right? There's no, if you take all the elements that are not in A and intersect it with all the elements in A, you're going to end up with the empty set. Well, what happens if we change this property? So this is 12. If you have A complement union A, so let's kind of say this out. All the elements in that are not in A and or all the elements in A, well, an element is either in the set itself or in its complement. So if you take the union of all of those, you're going to end up with our universe. So it's the universal set, right? And the last pair, I promise, this is the actual last pair. So in fact, I'll do these together. It says if you have A union B and then you take the complement of the union, it's the same as intersecting the individual complements, right? And then we can flip these around. There's another version of it that says if you take the complement of A intersect B, then this is the same as A complement union B complement, right? And these are the famous De Morgan's laws. De Morgan's a famous mathematician, did a lot of work with sets, and these are probably the most, well, certainly at an elementary level, the laws that are most associated with him. So I'm just going to prove one of these just so you can see it. So this is just the proof of this one. So this will, let me label this part A. So this is property 13, part A. So how do we show that two sets are equal? Well, what we have to do is to show that every element in this set is also an element in this set, and vice versa. Every element in this set is also in this set, right? So I'm going to say let X be an element in the complement of the union, right? Well, what does that mean? Well, if the element is in the complement, then it can't be in the original set. So this implies that X is not an element in A union B. So what does that mean? It means that X is neither in A nor in B. So it can't be in A. So if it's not in the union, right, then it can't be in A, it can't be in B, and it can't be in both. So that means X is not an element in A, and it is not an element in B. Okay, how does that help? Well, if it's not in A, then it has to be in its complement. And similarly, if X is not in B, then it has to be in its complement. So this implies that X is an element of A complement and X is an element in B complement. So that means, so this is, and again, the use of the word and here is important, right? Because this is saying that the same element X is in both A complement and B complement. So then it has to be in their intersection. So therefore, X is an element in A complement intersect B complement. So every element in the complement of the union is also an element in the intersection of the complements. Okay. And then the thing is, we just have to reverse this argument. We now have to show that if you take any element in this set, then it has to be in this set. But when you look at it, it's a very similar logic. It's just going in the opposite direction. That's the beauty in for some of the proofs with sets, is that once you figure out the logic in one way, you kind of reverse it and go in the other way. So similarly, I am going to let Y, I'm going to pick a different letter now. It doesn't have to be the same X, but let Y be an element in this set. So then that what this means is that Y is, since Y is in the intersection, then it has to be in both, right? So Y is an element in A complement and Y is an element in B complement. And that means that Y is not an element of A and Y is not an element of B. So then this is saying that Y is not an element in A union B, because it's not in both of them, right? It's the and that's important, right? And then therefore Y is if it's not an element in the union, then it has to be an element in the complement of the union, right? So what we've essentially shown is that these two sets are subsets of each other, right? So therefore, A union B complement is equal to A complement intersect B complement. And that's our QED, right? So again, this is the type of class where the proofs of these properties and some of the basic things we're introducing now are not like major course objectives, but I think it's important to see that all these properties have a formal proof behind them. And usually in more elementary classes, you tend to forego some of the proofs and so forth. But I wanted you to see at least one that involves using all the things that we've talked about, but in a more formal and general way. So those are some important set properties. I hope they made sense, and you'll use them in the future. And speaking about in the future, I will see you in another video.